In this video, we're going to look at a special group of exponential functions called hyperbolic functions. They're not going to look too much like exponential functions at first. This is called the hyperbolic sine function, and over here we'll write this, which is the hyperbolic cosine function. And the reason I say they're a special group of exponential functions is because this is defined as e to the x minus e to the minus x all over 2, and hyperbolic cosine is defined by e to the x plus e to the minus x all over 2. They're related to trig functions. A lot of properties for hyperbolic functions are similar to ones for trig functions, but they're also different in that they're related to a hyperbola instead of a circle, which does change some things, especially the sign of some of the properties. What we're concerned about mainly here is we're going to just find what the derivative of the hyperbolic sine function, the hyperbolic cosine function, and the hyperbolic tan function. And so maybe we'll write the definition of hyperbolic tan. And we're going to kind of do the lazy way. Just like trig, we can say tan is sine over cosine. Well, that holds true for hyperbolic functions as well. So this is hyperbolic sine of x over hyperbolic cosine of x. So we're going to go ahead now and find the derivative of each of these. And to do that, well, let's start by saying if y is equal to the sine h of x, then we want to find the derivative, then the first thing we're going to do is use the definition, because that is what the hyperbolic sine is. And that just gives us e to the x and e to the minus x to worry about, so we can easily take this derivative. We take out the half, which is constant, and leave it alone. The derivative of e to the x is e to the x, minus the derivative of e to the minus x is, well, that's e to the minus x, times the derivative of minus x, which is minus 1. And if we do a little simplification here, we're going to end up with e to the x, minus and minus gives us plus e to the minus x, all over 2. And depending on how quick you're looking around the screen, that should be familiar because that's the same thing we wrote right here. So the derivative of hyperbolic sine is hyperbolic cosine. Not a big stretch to believe that that's true, since the derivative of the regular sine function is cosine function. So essentially the same rule, and this is just a short little way to show that that's true. We're going to go ahead and do the same thing now for y equals hyperbolic cosine of x. We'll stick the definition in there. So e to the x plus e to the minus x over 2. And you might see that the same thing is going to happen here. We take the derivative, half comes out, derivative of e to the x is e to the x, plus derivative of e to the minus x is e to the minus x. Multiply that by the derivative of minus x, so that's the chain rule. That's minus 1. And if we simplify, well, e to the x stays, plus and minus gives minus e to the minus x, all over 2. And that is also up here in our definitions. That's hyperbolic sine. And here you should notice a difference, because the sine h of x is the derivative of cosine h of x. Similar to our trig functions, but not exactly the same. The difference, the negative. And that has something to do with the circles and hyperbola difference of being plus and minus. Nothing that we want to get into, but for us, this is what we want to know. The derivative of y equals sine h of x is cosine h of x. The derivative of cosine h of x is sine h of x. So the last one we're going to deal with here is the hyperbolic tan function, and we could define it in terms of the exponential equivalent, but we're going to do it with just the hyperbolic sine and hyperbolic cosine, since we know those functions already now. So if y is tan h of x, then we can say y is hyperbolic sine of x over hyperbolic cosine of x, and that's a quotient. So we use the quotient rule here, so the derivative then Derivative of hyperbolic sine is cosine h of x. Keep the bottom, which is cosine h of x, minus the derivative of the bottom, so the derivative of hyperbolic cosine is hyperbolic sine, and keep the top, so that's hyperbolic sine, all over the bottom squared, which is hyperbolic cosine squared of x. So there's our derivative. Let's simplify it and see where this is bringing us. That's cosine hyperbolic cosine squared of x minus hyperbolic sine squared of x all over hyperbolic cosine squared of x. And the top maybe has some warning bells for you. We should recognize this property, cosine squared of x plus sine squared of x equals 1, as our very common identity that we use for trig functions. Well, hyperbolic functions have a very similar property, and it's one we're going to use here, and it says that the hyperbolic cosine of x squared minus the hyperbolic sine squared of x is equal to 1. So notice the difference, again stemming from circle, hyperbola. And that's a good way to remember it. So here's property for hyperbolic functions. So if we go back here then, this is equal to 1 in the numerator over the hyperbolic cosine squared of x, and just like we would with trig functions, 1 over cosine h is secant h squared of x. The derivative of tan h of x is secant h squared of x, or hyperbolic secant squared of x.